So this is the one that says, I'll just let you look in your textbooks here. I'm not going to write it all down. But it says a farmer plans to fence a rectangular pasture adjacent to a river. So the pasture, I'll write down the key numbers here. The pasture must contain 180,000 square meters. It has to be our area, right? And he wants to, he's gonna fence this along the river, and so he's not a very environmentally conscientious farmer. He's not going to fence next to the river, and so, but he needs to minimize the amount of fencing that he's using, right? So we need a picture. What would the picture look like then? It's going to be rectangular, he tells us. Yeah. Okay, so we got to have, here's our river, right? Flowing along, and he's going to put his fence, something like that. We don't know the exact shape, but it doesn't matter. We need to get our variables though. What are we going to call the variables here? You decide. If this is the pasture that we're enclosing, yeah, we got X maybe and Y would define the area of this thing. Okay, so what are the steps we go through for an optimization problem? Step 1. Primary equation. So what is it that we're trying to minimize or maximize here? Okay, minimize fencing. We got a fixed area in this case, right? We're trying to minimize the amount of fencing that he needs to enclose this area. So what's that going to look like in terms of maybe a geometry formula? What is it that we're, I mean, it's kind of like a perimeter. Yeah, we'll call it, I don't know, what do you want to call it? We'll call it fencing, capital F of X and Y. Well, we don't say X and Y. Capital F is equal to what? What is the sort of pseudo perimeter here, the fence line distance? No, we're looking at 2y plus x. I've got y plus x. I don't need that side, right? So x plus 2y. Okay, so there's we got our picture. Do we need, what's the problem with that equation? Got two independent variables, so I have to have a secondary equation. There must be some constraint on this, right? That's going to give us our secondary equation. Now, what's the constraint? Area. Okay, so we know that area, which is just x times y, has to equal 180,000, right? Agreed? Okay. So we need to eliminate a variable by solving for it. And remember, the variable that we're targeting for elimination is the one that we want to isolate. Does that make sense? If I solve for x, then I can plug, for example, I can plug x in right there, and I'll end up with only the other variable, which is a y. In this case, does it really make a lot of difference? It doesn't really make much difference, does it? It's not like we've got one of these two variables squared. I mean, they're both about unequal foundation here. Doesn't make any difference. Arbitrarily, which one do you want to solve for? Y? Okay. So if we solve for y just equals then 180,000 over x. Let's put a box around it because that's our substitution equation. And that's what we're going to put in there, right? And what's that give us then? If we do that. We get f of x, right, equals x plus 2 times that. So 360,000 over x, which we could also, because we're going to do some calculus on this, let's write it maybe as x to the minus 1. Right? Because do we want to do a quotient rule on a function where I've got a constant on the top? No, we never do, right? Instead, we make it a negative power, so we don't have to go through that whole process of the quotient rule, right? So there's our function that we're going to differentiate. Now, there's one other important thing that we can't forget here, and that's the domain, right? And the domain is a little bit trickier here. It's not just mathematical; it's contextual. So, are there any values mathematically that don't work for this function for x. Okay, 0 wouldn't work, would it? But is 0 a likely option for us anyway? No, 0 is not going to make any sense anyway. So we know that our lower limit in this case is 0. We can't have a negative length, no such thing, right? And so it's going to be only positive. Now, what's going to be the biggest value of x? And talk to me about that. How are you going to figure out what the upper limit of our domain is in this case? Say it again.
Either 180,000 or
Okay, something, yeah. Now, a couple ways we can think about this. We could just look at our function and say, well, is there, it's difficult to do though. It's difficult to just look at the function. What's easier to do is to look at the constraint, because that's really what's, without a constraint, this thing would be easy. If I want to minimize the fencing, I'll just make it 0 and 0, right? But there is a constraint here. We have to have a certain amount of area. So if we look at the constraint right here, sometimes it's easier to say, okay, well, when I'm trying to maximize x, that's the same thing as minimizing y, isn't it? Because they're competing, right? They have an inverse relationship. As x gets bigger, y gets smaller, right? What's the smallest that y could be? I mean, it could approach 0, couldn't it? Right? As y approaches 0, what's x going to do here? Yeah, approach infinity. Now that might seem a little strange. It's not a very practical way to do it for the farmer, is it? But he could make that fencing go a really long ways along the river and just have the rectangle be very wide and not very tall. He's obviously not going to want to do that, though, is he? We're going to find a better alternative for him. So there's our domain. In this case, you know, any positive critical number is going to be the one that we're probably is going to be our answer. So now this ends up being a pretty easy problem, and I bet you notice that really, in a way, I think that the optimization stuff is an easier section than the other test, because once you wade through this stuff, once you wade through the process, which I think is kind of the fun part, that it's contextual, the calculus is, they're always simple. I mean, they're really, they're not these bizarre, you know, fractional exponents and things like I threw at you in 3.6. These are just regular old polynomials or rational functions that are pretty easy to deal with. So now here's our function. What's the next step? Now we shift into calculus mode.
Right.
Okay, differentiate, right? We got to get f prime. What's that going to be? 1
plus.
Okay, plus.
Negative 60.
Okay, I'm going to bring that negative 1 down. So let's just make it a minus. How about 360,000 x to the minus 2. Right? Okay. Do we want to take a second derivative here?
No.
It's up for debate.
It's easy.
I'd say yes, but you don't have to. You could just use the first derivative test. I think it's a pretty easy one to do. And really, what do we care about from the second derivative anyway? Well, it's going to impact, right? We're going to use the second derivative test. Are we really concerned with the values of the second derivative as much as sign? All we care about is the sign. So if we could, for example, show here real easily that the sign were always positive or always negative, that's all we would need. If I differentiate this, the derivative of 1 is 0. That goes away. What about the derivative of this? This is the same thing as minus 360,000 x to the minus 2. So what's that going to give me for that derivative? Okay, times negative 2, which is going to be some big positive number, right? So I know I'm going to get big positive number on the top. Maybe that's enough, divided by x cubed. But isn't x always positive, right? So really, we don't even have to do an awful lot with that, do we? Because we know that the second derivative on our domain is always positive, right? Right? That's probably good enough. I mean, we could be more particular. If you want to be more exact, you're welcome to. But we don't really need to, okay? So now we'll just take this information and go make our table. And you might be thinking, do we even really need the table? And you might be right. Oh, that's big. Okay, so if we just make our table then, oops. Okay, we said our domain was 0 to infinity, non-inclusive. We got to find our critical numbers. Here's our derivative function. That's undefined at 0. Is that a critical number? Marie's shaking her head no. She's right. How come? It's not in the domain anyway, right? So we're only looking for critical numbers that are in our domain. Now, if we set this equal to 0 and solve, that equals 1 minus 360,000 over x squared equals 0. Would you agree that's true if I add this to the other side and cross multiply? When x squared equals 360,000, right? And so x would just equal 600, plus or minus 600. But I only need one of those, right? Only the positive 600 is in our domain. And so we know that's a 0 of the first derivative. The second derivative is positive. So what is that? There's going to be a minimum, which is what we want. It's a minimum for fence line. And we got our answer. Almost. I guess we have to go back and find why. But the question is asking what are the dimensions, I'm assuming. Yeah, what dimensions would require the least amount of fencing? So we found that x is 600. We always go back to the box to get y. So y would equal 180,000 divided by 600, which is 300. So we get whatever our units were. I think they're meters. Right? Okay, make sense? Okay, now you guys, I have to admit I kind of lost track of the deadlines. I really didn't mean to bring that deadline on you. I apologize for that.